So the instrument itself, the nice thing about this instrument is we're making use of a lot of heritage, particularly the wire antennas have flown on Themis and the Van Allen probes. We're also making use of the digital component of the radio spectrometer that is currently being used on the Fields instrument for the Parker solar probe. So all of that is pretty nice. When you combine all of this together, this plot in the upper left is our version of what we believe we will be able to see with our instrument. So in other words, the bands here are different errors, different uncertainty bands based on the amount of integration time. And this is for the standard model. So this does not have any added cooling in it. So this is sort of the minimum model. We're able to make a good detection, you see, of these troughs. On the right-hand side is just some additional physics. Alpha is the added cooling rate if there's added cooling, and Z naught is the redshift that cooling would be on. The blue band represents the standard cosmology model, and the green is added cooling model. You can see here with the 1 and 2 sigma bands that we can clearly separate these two at greater than 5 sigma. So that would be very exciting to be able to do that. Well, let me move on to the second mission, and that is Farside, which is actually an acronym that you see here. Myself and my co-PI, Greg Hallinan at Caltech, have worked this last year with JPL and their Team X on the first engineering study of an array on the far side. The science problem is illustrated here, at least the part that we're looking at for the exoplanets. It's to recognize the effects of magnetic fields and weather, space weather on planetary atmospheres. Because some 2 billion years or so ago, Mars was, for example, was wet, had a substantial atmosphere, but when the interior cooled, the magnetic field shut down, then the solar wind began stripping the atmosphere, and that's measured today with the MAVEN spacecraft you see in the upper right. The atmosphere is still being stripped by Mars, and today Mars is a desert planet with no obvious life, at least on the surface, that we can see. So measuring the space weather and also the magnetic fields are an important ingredient in understanding whether or not planets, exoplanets, are habitable. So when we look out into the nearby part of our galaxy, what are the stars that are most likely to have habitable planets? Well, those are called M-dwarf stars, okay? You see from the histogram, this is simply the number of stars, and M-dwarfs dominate. These are smaller, cooler stars than the sun. And so the habitable zone here is about 2/10 of an astronomical unit. So they're closer. So the problem with these M-dwarf stars is they also burst. So here is a movie of a large solar flare from the sun on the left, about 45 times brighter than the mean, and boom, on the right-hand side, you see the flare from an M-dwarf star, 100,000 times. So you've got a couple of problems then for looking at habitability around M-dwarf stars. This is a highly stylized picture from my colleague Greg Hallinan of an M-dwarf star, also showing coronal mass ejections. So how do we detect this kinds of emissions? Well, we know from the case of the sun, when a coronal mass ejection comes off the sun, it's often accompanied by what we call type 2 or type 3 radio bursts. These are low frequency radio emission produced by the shock wave that is propagating out. And as that shock wave propagates out, the frequency that is observable goes to lower and lower and well below 10 megahertz. That shock wave also, when it hits the, in the case of the Earth or an exoplanet, it lights up the magnetic field, it energizes the magnetic field and increases the low frequency radio emission by orders of magnitude. So we have tools potentially to be able to investigate that space environment and magnetic field using low radio frequencies. All of the planets in our solar system with magnetic fields have low frequency radio emission, including the Earth. Jupiter is the only one that is visible from the Earth because it has a magnetic field that's strong enough to produce emissions above 10 megahertz. Everything else is below that, which is roughly 10 megahertz, is roughly the plasma frequency of the ionosphere. So we need to go to space to observe these exoplanets, we need a quiet environment. Here's some simulations, Claudio, that you have seen from a paper that my student Neil Bassett and I have submitted. This is observations at low frequency, both in orbit and on the surface. And what we've done, these are electromagnetic simulations, because the radio emission coming from the Earth, as you were showing, also diffract. That is, they bend around the moon, and that diffraction has to be taken into account. That shrinks the radio quiet cone just a bit. And these simulations indicate that in orbit for Dapper, we're able to be in the radio quiet zone about 35 minutes out of every 2 hours of the low orbit. On the right-hand side shows where on the surface of the moon we would be below 85 dB in suppression at both low frequency of 100 kilohertz, which we would observe for exoplanets, and then at higher frequencies that allows us to observe almost down to the poles. All right, the mission concept for Farside is shown here. We're going to operate at frequencies from 100 kilohertz to 40 megahertz. The idea is to use a commercial lander that will serve as a base station as well. We will deploy one or two or multiple landers. The landers in turn will deploy science tethers that have communication and power, and then the antenna nodes, of which there will be 128 of them, to form a radio interferometer. Here's our configuration. We're proposing to put this over a 10-kilometer diameter, which was nicely fit into Daedalus crater. And you see here, we're proposing to do this in a flower petal-like design, with the rover going from the base station, putting down these antenna nodes on one part of the flower petal where the red are indicated, goes back to the base station, restocks, and continues out. So depending upon a number of rovers, we can deploy the array in anywhere from 1 to 4 lunar days. The antenna node looks like what you see here on the right. The science tether not only has communication and power, but also has embedded within it a 100-meter wire antenna, tip to tip, that is used at the low frequency, as well as spacer antennas, which are 5 meters end to end for the high frequency. Each one of these nodes will also have a radioactive heater unit so we can operate at night. Speaking of operations, we have a number of good examples from the ground. Here's one from my colleague, Greg Hallinan at Owens Valley, the long wavelength array. LOFAR, the MWA in Western Australia, all have similar operations. Granted, these are at higher frequencies, several orders of magnitude frequencies, but nonetheless, we have good operational experience of such arrays. So we take all of this into account. This is a plot of the prediction of the sensitivity that we have for detecting the radio emission from magnetospheres of planets as a function of distance. And the colors in here represent just different models of how that radio emission will be enhanced by flaring from the stellar winds. And you can see that we have several dozen such planets are in view by this first generation array on the far side. We will use, we're proposing to use the Lunar Gateway to relay our data from the array back to the Earth, but other communication assets are possible. We've also been collaborating with Blue Origin and looking at their Blue Moon lander. I think Steve Squires is speaking next. Yes. You can see that this lander has capability of bringing over 10 metric tons to the surface. Got a couple of different rovers on the top. So the last image I want to show here is just a movie that we put together of the deployment of the rover off of a Blue Moon-like lander. That lander, as I said, will also have the base station. We will carry 2 RTGs for power. Here you see the rover also deploying the science tether, and a cartoon picture of then the stator antennas also being deployed. Power, telecom, and correlator will also be on the main lander. So last slide, summary and conclusions. Here is that I think all of the major space agencies recognize the potential of the moon and the Farside. It's important that we do these observations sooner rather than later. This is one of the things that I've been emphasizing. For all the reasons we've been talking about this morning. Let's get there, do these observations before we pollute ourselves. But even so, let's make sure that we maintain the quiet of the Farside. I'm not so much concerned about communication issues. I'm more concerned about leakage from the electronics on spacecraft in the vicinity in an orbit.
Absolutely.
That's where most of the background noise is going to come from. So with that, Claudio, I will stop there.
Thank you very much indeed. This was an excellent presentation and also encouraging all of us to keep our fight for the protection of the quietness of the Farside. Thank you, Jack.